The definite integral. Let's recall the definition of the definite integral. If the function f of x is defined on the interval a, b, then the definite integral of f from a to b is equal to the limit of the norm of the partitions go to 0 of our Riemann sums, provided the limit exists. All right, so here's some theorems to help us know how to deal with these. The first one deals with knowing when you can find that integral, when the limit exists. And it says that if f is continuous on your interval, then f is integrable on that interval. So you don't need to worry. You know the limit exists. The second theorem says that if your function only has finitely many points of discontinuity, that means there's only a finite number of places where there's a jump. And if f is bounded, that means that there's a number m such that negative m is less than your function and m is greater than your function on the interval, then your function is integrable on the interval as well. And the third one says that if your function is continuous and assumes both positive and negative values, then your integral is going to be equal to the area above the x-axis minus the area below the x-axis, which we alluded to in the last video. All right, so besides those properties, or those theorems, we have some properties that will help us know how to manipulate these integrals. The first one is called the zero width interval, and it says if your limits of integration are the same, then your integral is equal to 0. The second one is called the constant multiple property, and it says if you have a constant k multiplying another function in the integrand, then you can pull k outside of the integral. The third property is the sum difference, and says if you're looking at the integral of f of x plus or minus g of x, then that's going to be equal to the integral of f of x plus or minus the integral of g of x. The next property is called the additivity property, and that says if you look at the integral from a to b of a function and add on the integral from b to c of the same function, then that's going to be equal to the integral from a to c of the function. The next property is called the min-max inequality, and it says that if your function has a maximum value max f and a minimum value min f on the interval, then the minimum of f times the width of the interval is going to be less than or equal to your integral, and that'll be less than or equal to the maximum of your function times the width of the interval. The next property is called domination, and this says that if you have a function f of x and it's always greater than or equal to g of x on the interval, then the integral of f of x is going to be greater than or equal to the integral of g of x. And as a special case, if g of x is equal to the constant function 0, so if your function f of x is non-negative, then that tells you that the integral is also going to be non-negative. And the final property is the order property, and it says if you want to switch your orders of integration, then all you need to do is put a negative sign and go ahead and switch them. So this next slide is a graphical representation of the first 6 properties. The first one was the zero width interval where your limits of integration are the same. So that means I'm going from A to A. All I'm getting is a line, and lines have no area, so that's equal to 0. The second one is the constant multiple property. So this integral right here, the left-hand side, is the area under this curve here. And hopefully you can see that's just, here k is equal to 2. That's pretty much twice the area under this curve. So that would be 2 times the area under that curve. My third property is the sum property, and it's saying look at the integral from a to b of f of x plus g of x. So that's the area under this curve here. hopefully you can see that that's about equal, or that is equal to the area under f of x, so this sum here, plus the area under g of x here, which is this integral here. The fourth property was additivity, and that said if you look at the integral from a to b, so this area here, and add on the integral from b to c, so this integral here, then it's equal to, well, clearly it's equal to this whole area here, which is my integral from a to c of my function. My fifth property was the max-min property. Suppose this is where the maximum of my function occurs, and this is the minimum of where my function occurs. Well, clearly the area under my function y equals min of f right here is equal to the minimum of f times the width of the interval, and that's clearly less than the area under the curve y equals f of x, which is this integral. And that's clearly less than the area under this line here, which is the maximum of f times the width of our interval. And the sixth property was called domination. It said if you had a function f of x and it's greater than or equal to g of x, well, hopefully you can see that the area under the curve of f of x, which is this integral here, is definitely going to be greater than the area under the curve for g of x, which is this integral here. All right, so let's use, there's a few more properties before we go on. Let's see what they are. The first one says that if you're trying to find the integral from a to b of the function x, it's just going to be equal to your upper limit of integration squared divided by 2 minus your lower limit of integration squared divided by 2. The next property says that if you're trying to find the integral from a to b of a constant c, then that's just going to be equal to c times your upper limit minus your lower limit. And if you want to find the integral from a to b of x squared, then that's going to be equal to the upper limit cubed divided by 3 minus your lower limit cubed divided by 3. Alright, so let's put all these rules together to actually calculate some definite integrals. We'll do these four here. And as you can see, what do we have? We have a constant function. We have a constant multiplying a function x. Here we have the function 3x being added to the function 1. And here again we have a constant multiplying a function here. So let's see how to do that. The first one was the integral from 7 to 4 of the function 3, the constant function 3. So the first thing is, notice my lower limit of integration is greater than my upper limit of integration. It's often just easier to think about it with your lower limit being the smaller one. So I'm going to switch my limits of integration. I do that by putting a negative sign and switching the orders. Now since this is a constant, we know that that is going to be equal to the constant times your upper limit minus your lower limit. And here's our answer, -9. For our second problem, we're looking at the integral from 0 to 15 of 7x dx. And what we have here is a constant 7 multiplying the function x. So we had a property that said we could pull a constant outside of the integral sign. So this becomes 7 times the integral from 0 to 15 of x dx. And then we have a formula on how to calculate that. We said that's going to be equal to your upper limit squared divided by 2 minus your lower limit squared divided by 2. And when you simplify this, you'll get this as your answer. Our third problem was the integral from 4 to 1 of 3x plus 1 dx. So again, the first thing I notice is that my lower limit is greater than my upper limit, so I'm going to switch my order of integration by putting a negative sign first and then switching them. And now I have the function 3x being added to the function 1, so I can split that up into two integrals. So that becomes minus, and make sure you put your parentheses here, the integral from 1 to 4 of 3x plus the integral from 1 to 4 of the function 1 dx. Now to figure out this integral right here is a constant 3 times the function x. So we have a property that says we can pull the constant outside of the integral. And now we can go ahead. We have a formula to evaluate this, and we have a formula to evaluate that. This one says, okay, this is going to be equal to my upper limit squared divided by 2 minus my lower limit squared divided by 2 to give me this part. And this right here says, okay, it's a constant, so it's going to be equal to the constant times your upper limit minus your lower limit. And then once you simplify all this, you'll get your answer as minus 51 halves. For part D, we were looking at the integral from 1/2 to 2 of the function 5 times x squared dx. So the first thing we notice is that 5 is a constant, so we can multiply the function x squared, so we can pull 5 outside of our integral sign. And now what do we have? We have an integral from a to b of x squared. We have a formula for that. We know that's going to be equal to your upper limit cubed divided by 3 minus your lower limit cubed divided by 3. And that, when you simplify, gives you 105 over 8. All right, so let's revisit this idea of the average value of a continuous function. Now we're going to have f as an integrable function on a to b. That means we can find the integral. Then we're going to define its average value to be 1 over b minus a times the integral from a to b of f of x dx. So let's do an example. Let's graph this function f of x is minus x squared and find its average value over the interval minus 1 to 4. So the first thing we do is say, okay, the average value of f is going to be equal to this formula right here. Let's identify f of x, a, and b. We know that f of x is minus x squared, and we know ab is equal to minus 1, 4. So plugging those in, we get that the average value of f is equal to 1 over 4 minus a negative 1, the integral from minus 1 to 4 of minus x squared dx. We simplify this right here, and that gives me minus 1 over 5. And then here's a negative sign here. That's a constant multiplying, so I can pull that outside of the integral right here. And then I have from negative 1 to 4 of x squared dx. Now using our formulas, we know how to evaluate that. That gives me minus 1/5, 4 cubed divided by 3 minus negative 1 cubed over 3. And when you simplify that, you get negative 13 over 3 is your average value of f.